On May 21st, 2026, in occupied Kherson region, Ukrainian forces from the Security Service of Ukraine's Special Operations Center, A, struck a Russian FSB headquarters and destroyed a Pantsir S-1 surface-to-air missile system. The operation caused around 100 Russian personnel killed or wounded. Thermal footage from the strike shows direct impacts on the headquarters building and the air defense vehicle, with bright flashes and secondary explosions. Ukrainian intelligence located the FSB headquarters in the area and the nearby Pantsir S-1 system. The unit launched fixed-wing strike drones from Ukrainian-controlled territory. These drones followed low-altitude routes to the targets in the Henichesk area or along the Arabat Spit. The drones delivered warheads that struck the FSB headquarters and the Pantsir S-1 vehicle. The Pantsir S-1 combines 57 E-6 command-guided missiles with twin 30mm 2A38M autocannons. It operates as a short-range point defense system against aircraft, helicopters, cruise missiles, and drones. The system failed to prevent the strikes. The failure begins with detection. The Pantsir search radar, variants of the 1RS-1 or 1RS-2, uses the radar range equation. Received power decreases with the fourth power of range and depends on the target's radar cross-section. Modern strike drones use composite materials, radar absorbent coatings, and shaping to reduce radar cross-section to 0.01 to 0.1 meter square or lower. This reduction cuts detection range significantly compared to larger aircraft with radar cross-section of several meters square. Low altitude flight limits detection due to the radar horizon. The truck-mounted antenna sits at low height. Earth curvature and terrain features block line of sight. In Kherson's steppe and coastal areas, vegetation, buildings, and ground features create radar shadows. Ground clutter and multipath effects degrade target tracking. Slow or maneuvering drones produce weak Doppler returns that blend with birds or vehicle movement. When detection occurs, engagement relies on radio command guidance for the 57 E-6 missiles. The ground radar tracks both missile and target, then sends corrections. This link is vulnerable to electronic warfare disruption. Drones with terminal infrared, television, or anti-radiation seekers lock onto the Pantsir's emissions and switch to autonomous mode. Command guidance then loses effectiveness. The twin 30mm guns serve as the close-in layer. They face ballistic trajectory challenges against small, fast-moving targets. Wind, gravity, and prediction errors reduce hit probability in short engagement windows. Russian sources have noted limitations of these guns against small, unmanned aerial vehicles. Crew and operational factors contribute. Radars do not run at full power continuously to manage fuel, reduce emissions for anti-radiation threats, and handle maintenance. In occupied rear areas, systems often sit in static positions. Ukrainian intelligence identifies these locations and plans approach routes through blind sectors or masked terrain. The drones used low observability profiles, terrain masking, and terminal guidance to reach the targets. Strikes hit the FSB headquarters first, then the Pantsir S-1. Thermal video records the sequence of impacts and resulting fires. This outcome stems from differences between system design and current threats. The Pantsir dates to 1990s to 2000s engineering focused on larger, faster aircraft and missiles. Ukrainian middle strike drones operate in the 50 to 200 kilometer range band. They feature smaller size, variable speeds, low observability, and attritable production. These traits create saturation and precision challenges for legacy systems. Command guidance requires unbroken radar locks. Autonomous terminal phases on drones bypass this. Low radar cross-section and clutter reduce initial acquisition. Gun systems lack the precision kinematics for consistent small drone intercepts at range. Limited simultaneous target handling on single vehicles adds constraints. Russia fields many Pantsir units, but each costs $12 to $20 million. Losses force resource diversion to protect rear areas. Destroyed systems open paths for additional strikes on command nodes and logistics. The FSB headquarters loss removes a control center for occupation operations in southern Ukraine. Casualties among personnel increase pressure on Russian forces. The Kherson strike fits a pattern of Ukrainian operations against Pantsir systems. Earlier reports indicate SBU Alpha units targeted large numbers of these systems through 2025 to 2026 to create corridors in air defense coverage. Each success expands reach for medium and long-range drone operations. Scientific principles explain the gap. Radar performance follows the range equation. Maximum range scales with the fourth root of radar cross-section, transmitted power, and antenna gain. A tenfold radar cross-section drop shortens range by about 56%. Atmospheric attenuation, clutter rejection via moving target indication, and Doppler processing and sidelobe interference further limit performance in real environments. Missile guidance equations involve proportional navigation or command to line of sight. Target maneuverability exceeds correction bandwidth when drones execute evasive patterns inside the envelope. Electro-optical channels suffer from weather, smoke, or countermeasures. Gunfire control computers solve ballistic predictions, but small target size and high angular rates reduce probability of kill. Ukrainian drone designs optimize for these conditions. Airframes minimize metallic content and use planform alignment to scatter radar energy. Flight paths incorporate GPS and inertial navigation with terrain databases for masking. Warheads deliver focused blast and fragmentation against soft and semi-hard targets like radar arrays and missile launchers. Russian countermeasures include increased radar uptime, mobile repositioning, and layered defenses with electronic warfare. These measures spread resources thinner across occupied territory. Static headquarters protection remains predictable once located. The May 21 operation used coordinated drone strikes to neutralize both the command target and its dedicated air defense. Direct hits on the Pantsir disabled radar, launch rails, and vehicle mobility. Secondary explosions suggest stored munitions or fuel ignition. Broader implications appear in sustained Ukrainian pressure on rear areas. Previously safe zones in occupied Kherson now face regular threats. Russia must allocate more Pantsir and Tor systems to local protection, reducing frontline coverage. This shifts force balance in southern operations. Technical analysis of Pantsir engagements throughout the conflict shows consistent patterns. Low-altitude, low-radar cross-section approaches succeed when radar horizon and clutter mask initial detection. Terminal seekers exploit active emissions. Single-vehicle systems lack redundancy against multi-axis or sequential attacks. Future adaptations may include upgraded radars with better low-radar cross-section modes, laser or directed energy add-ons, or networked queuing from higher-tier systems like S-400. Implementation lags due to production limits and electronic warfare environments. Ukrainian forces continue iterative improvements in drone autonomy, swarm tactics, and electronic warfare integration. The strike data shows clear outcomes. Russian air defense in this configuration did not intercept incoming threats before impact. This reflects physics and engineering realities in modern drone warfare. Detection thresholds, guidance loop delays, and engagement kinematics favor well-designed small unmanned systems against 20-year-old point-defense architecture. Continued operations of this type test Russian rear area security across occupied regions.